Ni hao, and welcome to Taiwan, the land of night markets, bubble tea, and a whole lot of bike parts. This small island is responsible for producing over 60% of the world's high-end bicycle components, earning it the nickname, the Bicycle Kingdom. Decades of innovation and precise engineering have made Taiwan the go-to destination for top-tier cycling brands. Today, we're getting a backstage pass at FSA, one of the biggest names in the game. And unlike many brands, FSA owns their entire manufacturing process, from raw materials to the components that end up on your bike. And we're gonna see exactly how it all happens. From what I'm told, it means a lot of breaking stuff in the name of science, which I like. Now, FSA's factory is down in Taichung, about an hour south, so let's head on Taiwan's high-speed rail, make our way down there, maybe even grab a cheeky bubble tea on the way, because hydration is important, and I'm pretty sure tapioca counts as carbs. Let's go. Just like that, we're here in Taichung. Chances are, if you've ever had an FSA product on your bike, it was born right here. It's like a giant maternity ward for handlebars, stems, cranks, wheels, and a whole lot more. FSA have just launched their new Gradient lineup, which is being made behind these walls as we speak. Now, I don't know much about the business of making bike parts, but from what I'm told, it involves robots, laser beams, and possibly some explosions. Oh! So, let's head inside, meet up with our friend Mark, and get a lowdown on how all the magic happens. See you in there. So before the products go out there in their physical form and get tested, you can actually test them virtually with computers?
Yeah, so what we're going to do here is that we're going to take the designs that we've created and engineered. We're going to look at those designs as three-dimensional models within the computer itself. Then we're going to run some FEA, finite element analysis, on the computer program itself.
Explain like I'm 5.
Yeah. So basically, it's going to check the computer. The computer's going to check it to see, is it strong enough and stiff enough? Does it perform how you want it to perform?
So how long on average, I know this is tough to answer, but does a product spend on the screen before it goes?
So it can go quite quickly if you've got pretty good agreement about what you want for design, what you want for shape. You know, within a week we could have, we could go from the idea stage all the way through to having a final design in order to have it ready to go. Now that doesn't mean you've got it released into the market, but that at least gets us going to the next step.
Okay, so Mark, we've seen everything on a computer screen, but this is where it comes to life.
Exactly, yeah. So this is where we take all the designs that we've come up with and we turn it into reality. And specifically in here, we're gonna take a look at some machining and some CNC work that we do on aluminum.
Okay, and what does that entail? Like, what are we talking, headsets to cranks, everything?
We're talking headsets, cranks, bottom brackets, chain rings, hub parts, pretty much anything that's going to be alloy that's gone on the bike itself, we're going to be doing in here on CNC.
So I have a question specifically about the cranks. Why are we bonding them as opposed to a forge or another type of manufacturing?
So we are forging, we're forging, then CNCing, and then bonding.
See, this is how much I know.
And the reason we're doing that is to get something that's going to be optimally stiff for what the use is. In this particular case, it's going to be for a trail enduro type product. And then we're also trying to get the weight down as much as we possibly can.
Now, my pea-sized brain, when I hear bonding and gluing something together, I'm thinking like Elmer's white glue.
Yeah.
It's not that.
No, not at all. So we're using really aerospace grade bonding agent. We've done precision machining between the crank pieces themselves that are going to be able to account for what the tolerances are for the bonding agent. It's going to kind of put things together and create the best possible crank for us.
Roughly in a day, how many crank sets can you guys pump out?
Like 1,000.
What?
So
you say like 100. Oh my God.
Yeah, 1,000. So, and it really depends on, different times of year we're ramping up for different production. So, but what we could do for what our process is, we could put 1,000 cranks together.
Oh my God. Yeah. All right, well, let's go take a look.
Let's go take a look.
All right, Mark, now where are we?
Okay, so we're going to take a look at the gradient crank machining a little bit closer. This is the forged blank that we're using.
Okay.
What's going to happen here is we're going to put this into the CNC machine and we're going to be able to machine the interior structure as well as the exterior structure. We're also going to machine the groove section where we've got the interface between the outer and the inner of the crank arm, and we hold that tolerance to 0.007 millimeters. So yeah,
oh my God,
pretty precise.
0.007.
Yeah, 0.007. So what you're going to see here is that we're doing the machining for the crank arm itself, both the outer and the inner. You'll see this is the part before it goes into the CNC, and we'll show you in a few minutes what the part looks like coming out of the CNC.
Very cool.
So yeah, so we're going to do both the outer, the inner. Then we take it, we bond it upstairs, we bond it, put it together. Comes back downstairs here, and we're going to do the final machining on the outer shape itself. Takes off the bonding agent as well as does all the finishing work. So for this particular process here, I mean, this is really going to be, you can see the gear ratchet system, the helical coil there. So the machining on this is going to be, it's called power skiving is what the machining process is. And it, you know, it basically combines two different processes, both lathing and milling. And so it gives us faster cycle time, better efficiency for production, and then we can also control the tolerances a lot more. So especially with our hub ratchet system, you can see the free hub there. So the forged blank kind of comes through the machine, and then from those forged blanks, we're able to machine out to any of the free hub shapes themselves. So there you can see one of the integrated free hubs. You know, through the power skiving process, we're able to machine the helical coil plus the free hub shell itself. What we're doing here is we're taking the inner and the outer half of the gradient crank arms. They've basically been shot peen sandblasted on the inside to allow for a little bit better adherence with the bonding agent. Then they're heated up first so we can minimize the thermal shock that we're going to get. Then they're put into the machine here, and then there's precision application for the bonding agent between the tongue and groove joint kind of that we had seen earlier, and then they're put together here at the final process.
So by the end of this room, you have a crank ready for anodizing.
You've got a crank ready for machining. So yeah,
so this more?
Yeah, so there's more. So what we'll do is we'll take the finished crank after it's been bonded, bring it back downstairs, and we're going to do some additional machining on the outside, and that's going to get us to that final shape. And so, you know, then you're going to be able to take that, and then that goes out for anodizing, logo application, and then finally assembly.
Yeah.
So here we are. So
much happening.
So yeah, we're lasering a lot of different product right now, but we've got gradient chainring here that we've already done the machining, we've already done the anodizing.
So can you laser etch anything, any design?
Pretty much any design. The only limitations you're going to run into is obviously the space and size of the product itself, and then if that product has any complex contours to it, and then you're also going to have some limitations on size depending on the resolution that you want to get with your laser etch itself. But generally, yeah, we can pretty much make anything.
And is this the final step before we get to QA check?
Yeah, so this will be one of the last steps you're going to get to. From here, it's going to go through final QA, then it's going to get packaged and put in the product for shipping.
So Mark, we've forged, we've bonded, we've CNC'd, we've laser etched, we've done a lot of stuff. Before the products go in the box, they come here.
Yes, so we're going to do QA, QC, basically quality assurance, quality checks on all the products that are kind of coming in and out throughout the manufacturing process. And then we're verifying to make sure that everything's going to meet the tolerances that we've set up on all the dimensional spec.
Okay, and I'm seeing a lot of products in the wall.
Yeah.
Are those the golden eggs?
Those are the golden samples is what we call them, pretty close, yeah. So what those are going to tell us is that that's, you know, kind of the default, what we're setting the standard to make sure, like, does the product not only look how it's supposed to off of what's there, but then those products are also going to have all the correct dimensional spec as well.
Okay, so this is the room where everything gets checked dimensionally. But next is the testing area, correct?
That's correct, yeah.
And not every product makes it out of there alive?
No, not at all. That's where we're going to go break some stuff.
Oh my God, yes. Okay, let's go break stuff.
Let's go do it.
There's a lot happening in this room that involves breaking things, stretching things, twisting things, correct?
Yes, so basically this is our test lab, and we're going to do everything here to find out what's the ultimate strength of our performance of our product. So we've got a lot of fatigue test, impact test, strength test. This section here is going to be our wheel fatigue test. Ooh. So we're going to basically be running wheels here to find out the duration of the hubs, rim stability, spoke stability, and ultimately find out, you know, did we build the wheel to the tolerances and the expectations that we set up.
And like, to be clear, you're not putting every product you make through this room.
So every batch that we're going to manufacture, we're going to pull out a random percentage, and we're going to check that and test that. So, we're trying to make sure that we're building the best possible product. This lab is running 24/7. There's always something running in this lab.
It's a bad place to be a mountain bike product or road product.
Yeah, you're not going to make it very long in here.
All right, so fatigue testing is all well and good, but what I want to see, and what I know a lot of people want to see, is stuff break.
Yep.
Where does that happen?
That happens back here, and that's the impact testing. Let's go take a look.
All right, so what products are first on our hit list?
So what we're going to take a look at today for impact test is the new gradient wheel set and also the new gradient handlebar. So we look at fatigue, we look at manufacturing, but what we really want to take a look at is like, how do these things handle in the most extreme conditions? And sometimes the only way you can find out is by breaking stuff.
Sounds like a good plan to me.
Let's do it.
Okay. This is 100 joules. I don't know how much that is. Oh my God. Ooh. Still safe. So we're at 120 joules. The standard is 40. So this is a lot. This is a big huck to flat. It's like one of those rides at an amusement park that just slowly goes up and then drops you. Oh my God. So we're just gonna keep smashing it until it fails. All right, I'm super qualified to do this.
Nothing.
Guys, it's too strong. It looks good. Temp 4. If this doesn't do it, it's indestructible. Still true.
Yeah.
Still straight. So the wheels are good to go. They're gonna rig up the machine to test handlebars instead. And I'm really hoping this time something breaks. Oh God, it's so violent. Oh God. Oh, it's so high. Oh, okay. It's good? That's it?
Yeah.
It didn't break?
Yeah, it didn't break.
Can we break it? All right, so we put it through the normal test, all the way up to 140 joules of energy, going through those carbon bars. It didn't break. I need carnage before I leave this place. I asked our friend Stu here, the engineer, he's just gonna ramp it up. We're gonna break the bars. 151? Yeah. Oh, we're going higher, okay.
You want to see it break.
You're a madman. I'm so scared. Oh, very exciting update. We did break something. Take a look. Oh God, how did you lift this, Stu? Jesus Christ. There we go, boom. That is a broken carbon bar, but that was after 151 joules through the bars, and that was the same set that went through all those other tests. So this is not a fresh bar anymore. Honestly, not as catastrophic as it could be. The bar's still there, your hand would still be on the grip. Super impressive. It's quitting time here at FSA, but I will say that was a pretty successful day. We got to see the entire life cycle of a product from computer screen to physical to on its way to you. And I hope the next time you ride your bike, you think about all those processes and how they all came together to make what you're riding down a trail. As for me, I gotta get back to Canada, maybe a quick bubble tea along the way. Let us know in the comments what factory we should visit next. We'll see you there.